are two different methods that can be used when you're evaluating definite integrals that require substitution. So we're going to look at both methods, and what I suggest is just get good at one of the methods, whichever one you liked better, and then always do it that way. Don't mix them up, because when you mix them up you get confused. That's what I've noticed with students, and honestly one is not better than the other. It just really depends on what you like. There is no shortcut. They're both equally as long. So the first method, what you would do first is you're going to change everything in terms of u to work the problem out. The second method is you're not going to change the limits of integration, and you'll go back into x to solve. So for the first method, we're going to make everything in terms of u and solve it without getting back into x's. In our second method, we're actually going to get back into x's because we're not going to change our limits of integration. So these problems require substitution, so we're going to start off just like we would any substitution problem. What should u be? Well, u should be what's being raised to a power, that function that's being raised to a power. So in our case, u is going to equal 2x cubed minus 1. Well, if u is equal to 2x cubed minus 1, the derivative du would equal 6x squared dx. Well, notice I don't have a 6x squared dx, I just have an x squared dx. So I divide both sides by 6. Remember, there's an implied 1 there. So then I know that 1/6 du is equal to x squared dx. Well, I'm also going to change my limits of integration before I rewrite my integral. So my current upper limit is 1. So my new upper limit, so when x is equal to 1, we know that u is going to equal 2 times 1 cubed minus 1, because u is equal to 2x cubed minus 1. So working this out, I end up with u is equal to 1. And my new lower limit of integration, well, my current lower limit of integration is 0. So this would be, for us, u would equal 2 times 0 cubed minus 1. Well, 2 times 0 cubed minus 1 is negative 1, so my new lower limit of integration is negative 1. So remember, we have currently the integral from 0 to 1 of, and I'm just going to rewrite it as 2x cubed minus 1 to the 4th times x squared dx. So making in our substitutions here, we know that our new lower limit of integration is equal to negative 1. We know that our new upper limit of integration is equal to positive 1. 2x cubed minus 1 is equal to u, and that gets raised to the 4th power. And my x squared dx is equal to 1/6 du. Well, now I'm going to finish this whole problem out without ever putting my x's back in, because I've changed my limits of integration. So this is going to equal, well, 1/6 a constant multiplier, it multiplies along. Here my n is equal to 5, so I'm looking at times 1/5 u to the 5th, evaluated from negative 1 to 1. So if I move us right over here, I get 1/30 u to the 5th, evaluated from negative 1 to 1. Plugging in the upper limit of integration, I get 1/30 times 1 to the 5th, minus, plugging in my lower limit of integration, I get 1/30 times negative 1 to the 5th. Grabbing a calculator to work this out, so you're looking at 1/30 times 1 to the 5th minus 1/30 times negative 1 to the 5th. And you end up with, making that a fraction, 1/15. So the integral from 0 to 1 of x squared times 2x cubed minus 1 dx is 1/15. So we're going to do the same problem because the next one is the same problem, but we're just going to use the other method. So this changes everything in terms of u. Our other method won't change the limits of integration. We'll go back into x to solve this problem. So the first thing we want to do is, just like the last one, identify what u should be. Well, again, u is going to be our 2x cubed minus 1. If u is equal to 2x cubed minus 1, our derivative du was equal to 6x squared dx. Remember, we don't have a 6x squared dx, so we divide both sides by 6, and we get 1/6 du is equal to x squared dx. Then we say, all right, well, let's rewrite that integral. So we're looking at the integral from 0 to 1 of 2x cubed minus 1 to the 4th times x squared dx. And this then becomes the integral from x equals 0 to x equal 1 of, well, that 2x cubed minus 1, recall, is my u, and I'm raising it to the 4th power, and then this x squared dx is considered to be my 1/6 du. If I integrate this, I end up with 1/6 times my 1/5 u to the 5th, and I'm evaluating it from x equals 0 to x equal 1. So we're looking at 1/30th. Let's get back into x's. My x's, remember, are my 2x cubed minus 1, because u is equal to 2x cubed minus 1, raising that to the 5th, and then I say evaluating it from 0 to 1. So then we just plug this all in. So the upper limit of integration, so you're looking at 1/30th times 2 times 1 cubed minus 1, minus, plug in that lower limit of integration, so you're looking at 1/30th times 2 times 0 cubed minus 1. And you're still using a calculator for this. So you say 1/30th times 2 times 1 to the 3rd minus 1. And all of that subtracted from, and then 1/30th times 2 times 0 to the 3rd minus 1. And we end up with the same answer of 1/15. So this is equal to 1/15. So no matter which way you do it, you end up with 1/15. You either change the limits of integration first, or you're technically changing your limits of integration when you go back into x. It doesn't matter which one you choose. I typically change my limits of integration, so that's how I'm going to do the rest of the problems. But if you liked method 2 better, then you can stick to method 2 every time you do one of these problems. So let's continue on with more examples of this. Evaluate the following integral. Well, again, I never like it when I see a square root, so the very first thing that I'm going to do is I'm going to rewrite this as the integral from 1 to 3 of 12x times 3x squared minus 2 raised to the 1/2 dx. So since 3x squared minus 2 is raised to the 1/2, that's what I'm going to let u equal. And if u is equal to 3x squared minus 2, then my derivative du would equal 6x dx. But I don't have a 6x dx, I have a 12 dx. So to get 12, what I need to do is I need to multiply both sides by 2. So I end up with 2 du is equal to 12x dx. So now changing my limits of integration, I would say, okay, my current upper limit is 3, so x equals 3 in terms of u. Well, that would be u equals whatever 3 times 3 squared minus 2 is. So 3 times 3 squared minus 2 on a calculator, you end up with 25. And your new lower limit of integration, so my current lower limit of integration is 1. So you're looking at u equals 3 times 1 squared minus 2, and then grabbing the calculator to work that out. If I hit second and enter and make my 3 into a 1, I end up with the number 1. So then, recall this is equivalent to the integral from 1 to 3 of 3x squared minus 2 to the 1/2 times 12x dx. Therefore, if I'm doing my substitution, I know it's going to be the integral from my lower limit of integration is now 1. My upper limit of integration is now 25. 3x squared minus 2 is my u. It's still raised to the 1/2. And my 12x squared dx is equal to my 2 du. So working this out, this ends up becoming 2 times, so that's going to be 1 over, here again my n is equal to 1/2. So this is going to be 1/2 plus 1 is 3/2, u to the 3/2, and this is evaluated from 1 to 25. So if I grab a calculator and figure out what 2 times 1 over 3 over 2 is, I end up with 4/3. So this is really 4/3 u to the 3/2 evaluated from 1 to 25. So plugging in that upper limit of integration, we're looking at 4/3 times 25 to the 3/2 minus plugging in that lower limit of integration, 4/3 times 1 to the 3/2. Sticking this in a calculator, so we end up getting 4/3 times 25 raised to the 3/2 minus 4/3 times 1 raised to the 3/2. And we end up with 165.333, which as a fraction is equal to 496 over 3. All right, let's go ahead and do example 9. More of the same. So here, I'm going to let u equal my denominator, which is x plus 1. If u is equal to x plus 1, my derivative du would just equal dx. Perfect, because that's all I have. I'm going to change my limits of integration. My new upper, my current upper limit of integration is 1. So in terms of u, I'm looking at u is equal to 1 plus 1, or my u would be equal to. My new lower limit of integration, my current lower limit of integration is 0. Therefore, this would be u is equal to 0 plus 1, which is just equal to 1. So then if I transform this whole entire integral, we're looking at the integral from 1 to 2 of 1 over x plus 1. Recall that this is equal to u, and then du. Well, the integral from 1 to 2 of 1 over u du, well, I know that this right here is going to be the natural log of the absolute value of u, and now this gets evaluated from 1 to 2. So plugging in my limits of integration, I'm looking at the natural log of the absolute value of 2 minus the natural log of the absolute value of 1. Well, I know that the natural log of the absolute value of 1 is equal to 0, so that just cancels. So this is equal to the natural log of 2, or as a decimal, it's going to be 0.693.